conservation of momentum in 2 dimensions. Super essential for spaceflight and for doing well in physics exams. So what is conservation of momentum? It's defined that the total momentum of the system remains constant, provided no external forces act on it. And in space, generally, there aren't external forces. In simple words, if we look at a collision or some sort of interaction, if I take the total momentum of all the objects before the collision or interaction, they're going to sum up to the total momentum afterwards. But first of all, we need to understand it can be applied in 1 dimension, a straight line, 2 dimensions, if I've got some sort of x and y, or even 3 dimensions, which generally things work in. Momentum is defined as the product of an object's mass and velocity. So that means you take the mass of the object, you multiply by its velocity, you have its momentum at that given time. So the 2 situations, you can apply it to a lot, but there's 2 very common situations. One is a collision, and we're going to show a very, very simple short experiment that helps us to understand the principle of conservation of momentum. And then, obviously, we need to apply it to spacecraft expelling hot exhaust gases. Now let's look at its key case, the use in rocketry. So we have a rocket, and every second it's expelling m kilograms of mass. And that has an effective exhaust velocity, in this case to the left, of VE, relative to the velocity of the spacecraft. Now I'm just showing it not moving. In reality, it's going to be moving to the right, and we're just looking at the change in momentum. So that rocket gas of mass m moving to the left compared to the spacecraft of V has a change in momentum or magnitude of mve. But according to the law of conservation of momentum, the spacecraft will have an equal amount of change in momentum in the opposite direction. Now we show the actual spacecraft moving much slower. That's because its mass is much greater. Now in reality, this is not an individual expulsion of gas. This is happening at a constant rate, and we normally say the mass per second, or we could take a different time period. So it's going to continue to accelerate. But what makes it complicated, as you expel gas, the mass of the spacecraft decreases, so its change in velocity goes up, its acceleration increases. So why do we need 2-dimensional or even 3-dimensional momentum in rocketry? Well, imagine this is the inclination that we want to launch at. There's a slight problem though. There's land in the way, and you don't want to launch over land. If there's a problem, if you have to terminate the flight, it could be very dangerous. So instead, you launch at a different inclination. We call this a dogleg. And there we are. We can see the track. The track is missing the land. Then, what does the rocket do? It needs to reorientate, or yaw, in this case, to the right. So now it has a component both parallel to the direction it's moving and perpendicular, if you like, a y and an x. And what happens? This allows it to follow the track and eventually end up on the right inclination.